So first of all, thank you very much. Good afternoon to everyone. Actually, funny thing, I was waiting for this since morning 9 o'clock. I think okay. Then I didn't realize it was a Pacific Day time. So I thought missed the whole meeting, so I couldn't get onto the Zoom. Anyway, I'm here. It's a pleasure, and thanks to all of you who organized this one. And this is the work we did almost 2 years ago. We don't have anything new about this. I gave this talk before. So our goal was to actually go in search of a different platform for looking for the Majorana. It started with the theory input, and then we went on and explored the possibility of seeing that in the surface state of gold. So there are several people who are involved in the project, as you listed here. And it actually started with Patrick Lee and this grad student at the time, Henry Potter. They approached us, and then I had the postdocs, Peng Wei and Sujit Manna, in different times. And they took part in this, and they were the ones who actually created all the experimental results. And the modeling was done by Yingbing Shi and Cam Law in Hong Kong University. So this is the work we're going to present, what we have using our scanning tunneling microscope, how we can locate the Majorana pair. Sorry, yeah, I messed up. Okay, so we know this, so this whole meeting is on Majorana. I don't want to go into all this introduction, which we know very well. Before it all started many years ago, several people are involved, and in particular, Kitaev's prediction that one can have in a special superconductor the fermions split into two parts, well separated in space, and these are called pair, zero modes. And there has been a lot of interest in this for the last many years, as you know. And one of the major reasons is, of course, besides the physics of it, it's possible for actually creating a robust topological qubit with this kind of system because of this stability against any kind of source of decoherence. So we were approached by Patrick Lee and Andrew Potter, as I mentioned, and they came to us and told, okay, we have a scheme here, we have a theory here, which might lead you to seeing Majorana. All you have to do is to drive the gold into superconducting state and look for the Majorana. That's what they said. So that was something very new for us, and it's a very different area. Then, okay, let's take the challenge because we believe this theory must be good because they are very confident that we should be able to see it. And also it is a system which is which one can create easily, as you'll see as we go along. So the theory said that the Shockley surface state of 111 gold, if you can induce superconductivity, that it can be a nice platform for creating Majorana pair. So essentially what you have is couple that to a conventional superconductor, this gold, bulk gold, and the surface state, you can say superconducting. Then you narrow down the wire, as you can see here. 1 second. Okay. As you narrow down the width of this strip, then you can see the edge modes developing. They're localized and they're actually going closer to the zero energy. So depending on the length and the coherence length. So basically what you have to do is create a one-dimensional wire, and then in superconducting state, we should see this Majorana. So what are the needed ingredients? First of all, you have to have superconductivity and large spin orbit that drives them into the purely superconductor. And of course, we need to have a large magnetic field to go for this topological gap regime. So that was the idea. And then we, as I mentioned, we have a team of people. Theory, as I said, Patrick Lee and Andrew Potter, those are theorists, closely working with us on this program. And started with the Peng Wei. He's now a faculty in UC Riverside. He's still closely collaborating with us in another program. And Sujit Manna was a postdoc on the scanning tunneling microscopy, and he's a faculty in the Indian Institute of Technology, Delhi. And the model is done by, as I mentioned, KT Law, Yingbing Shi, student in Hong Kong's University of Science and Technology, along with Patrick Lee. So we have a couple of papers on this one, and patent application in process. So currently, the two other postdocs who are working on this, Yasen Hu and Alessandro Luardasani. So these are two people we just started again back in this program. Okay, so there are two things involved here. One is this gold surface state is, as you can see here, the surface state band is isolated from the bulk band. So which means the superconductivity in the surface state is by indirect means. So to create a superconducting surface state, first of all, you have to get the bulk to be superconducting by proximity, and then you have to have some sort of interband scattering process. There are several possible mechanisms. One is elastic scattering, or you can have inelastic scattering involving such as phonons, or you can also have scattering of pair across the bands. So in all these processes could be taking part. Then that leads to the surface state to become superconducting. That was the initial theory by Patrick and Andrew. So then, of course, what we had to do is couple this gold into conventional superconductors, any aspect superconductor. Then you can look for this surface state superconductivity. That's our first goal. Once you have this superconducting surface state, gold 111, one should be able to host the Majorana pair. Now we know that, of course, there are lots of work that have been published in the last 10 years. Most of them are either on semiconductors or on STM-related magnetic layers, again, atomic layers. And of course, just now we heard another talk on the vortex state in the superconductor. So what we wanted to do was to find a system which is not only stable and easily achievable, but also it's a scalable system. And besides that, it needs to have a large energy scale. So that was the goal, and this gold system seemed to be the right candidate for us to pursue. So that way, we think that the story for the Majorana is continuing, and we are seeing some very promising results based on this gold system, as you can see as we go along. Now, briefly, the outline is to just again tell you about what the theory is expecting and what are the challenges we have to actually reach there. The next is, of course, to create this layering system. For example, get the gold 111 very cleanly coupled to a superconductor, and it still should maintain its surface state. Then induce superconductivity. And one of the major things, as you'll see, is the tuning of the Fermi level. It is very, very important because the Fermi level in the case of surface state is way up compared to the bottom of the band. So then looking for the Majorana signature, and then, of course, which direction we can go towards the topological qubit. So the theory said, of course, you have this surface state, which is isolated from bulk, but the bottom of the band to the Fermi level is about 0.5 eV. That's a huge amount. So in order to see the Majorana, we need to go closer to the edge of the band. Otherwise, we have to deal with many, many modes. So having too many modes actually dilutes the possibility of observing the Majorana. So that was the biggest challenge. The nice thing about this gold system, it's spin-off, its Rashba spin-off rating is on the order of 110 milli-electron volt, which is like 1,000 times bigger than what is available in the case of semiconductors. So that way we can right away know that we have a system which can be actually create a very robust Majorana. So, but the problem is the Fermi energy is very far. And secondly, of course, in order to see the Majorana, you have to apply a large magnetic field. If you go for the STM-based tool, then you need to have magnetic field very large to be applied in the plane of the film or along the nanowire. So the maximum field what we have is 5 Tesla. It's a parallel field, it's a vector field. So that's again another limit. So given these two things, solving these problems is non-trivial. Now, what we found out was magically European sulfide, when you put on this gold surface, it actually allowed us to reach both the goals. First of all, it reduced the Fermi energy way down all the way to about 30 milli-electron from the bottom of the band. That means you don't have to deal with a huge number of these modes. We just have few modes. For example, if it goes down to about 30 milli-electron volt, then you just have to deal with about 5 modes, subbands crossing the Fermi energy. So that actually gives a better probability for seeing the Majorana. And the second thing it does is this European sulfide with a large exchange energy, large exchange field at the interface, creates a Zeeman field, which actually helps in achieving this Majorana, topological gap state. So this is exactly what we're able to do with having European sulfide on the top. So that was a very good sign for us. So as we went along, we could actually reach what was expected from the theory. So our goal was to create ultra-thin 111 gold on a superconductor, then induce superconductivity on the surface state, look for it, then of course reduce the Fermi energy all the way down, and then of course you can scale this into any kind of architecture you want. It's nice to actually make a circuit out of this. So applying a gate is ruled out because the energy is too large to move. So the only way you could do was by changing the surface dielectric. So we were able to grow the gold, ultra-thin gold on the vanadium. This took some time for us to actually achieve because first of all, we had to have the right kind of material, which has right about a finite TC, so that it allows the gold to grow 111. So we were able to do that in the MBE ultra clean condition with a good coupling of the gold 111 into the vanadium 110. Then you can see both the reed pattern and also XRD. Look at all the kissing fringes. So we do have a very flat, very clean interface. And that may be actually very helpful for us to actually look for the very good properties of the surface state of the gold. So this is actually also supported by the STM studies. So now we have a 20 nanometer of vanadium, and you can see the flatness here at the larger scale. Then you zoom it down, and you can see actually 110 of the vanadium forming. So this quite nicely matches that of the XRD result. Now you put gold on the top, you can see the gold almost starts covering completely by about one monolayer, as you can see. You know very well the gold growth is non-trivial on any metal surface. So we were able to adjust the growth parameter such that we could see this very nice uniform coverage. So when you have a 4 nanometers of gold, you can see nice atomic structure of the gold 111 on the surface. So it shows very well ordered, very clean gold surface. At the same time, it's also 111 as you expect. So now we have a very nice gold layer on top of the vanadium. Vanadium is a superconductor with a TC of around 5 Kelvin. Now, another thing, of course, we want to make sure that the surface state is still intact. So we can use STM to actually study the surface state. And you can see the tunnel conductance. As you find here, this is a schematic of the tunneling. And you have the surface state gold, and then you move the band with respect to the other electrode. Then you find that there's a singularity developing in the tunneling conductance. So this singularity has been attributed to the surface state onset of the gold. So it's about 1.55 EV, which is close to what is seen in the past by various techniques, photo emission and all that stuff. So we do have a nice surface state still persisting on the surface of the gold. So we do have now 4 nanometers of gold with a nice surface state on the vanadium, as you can see. So this thickness of the gold, which shows so that it's just about the same value or less than that of the coherence length. At the same time, it's bigger than the surface state penetration depth. So we could make a very nice flat films. So it has nice surface state, and this coupling of the vanadium actually creates superconducting. To show that the surface state is indeed superconducting, so we resorted to actually planar junctions in the beginning. So this was done by creating this kind of planar junction structure, as you can see here. The growth of vanadium is on sapphire, and then you have gold on that, and the barrier is made up of European sulfide, and top electrode is aluminum, which is also a superconductor. Now, as you can see, as a function of temperature, at about 4 Kelvin, where the vanadium is superconducting, you can see the tunnel gap opening up here. As you cool down, what you see is the gap actually develops into a well-defined peak, coherent peak. As you go below 2 Kelvin, you can begin to see an additional step forming. Below about 3 Kelvin actually already. So you can see the additional peak forming. So basically what we have is vanadium superconducting, and as you go cool down, of course, that also drives the gold bulk into superconducting state. Then as you go down below 3 Kelvin or something, then you can see the surface state also showing superconducting. The additional step is related to the surface state gap. Now, as you go below 2 Kelvin, that means you go below the TC of the aluminum also, then you have what's called SIS tunneling. So when you do the growth, measurement at 1 Kelvin, where both the gold and aluminum superconduct, you can see multiple peaks on each side of the zero bias. So these peaks are very well explained by both the surface and the bulk superconductivity of the system. So here is a schematic of what we think it is. So that's a superconducting aluminum, a nice defined gap, and we know the gap of the aluminum. And at the same time, of course, from these peaks, we can determine what the gap of not only aluminum, also that of this gold, bulk, and the surface state. Here are the numbers we get by fitting the data into SIS tunneling. So gold bulk is 0.61 EV. Aluminum gap is, of course, the typical BCS gap, 0.22, whereas surface state has a very nice gap of around 0.38 MeV. So this is nice compared to that of the vanadium, which is way underneath the system. So we are able to actually proximity couple the gold into superconducting state, and not just that, the surface state shows a nice gap. So we have a very nice system now, which is surface state is there. At the same time, you also have this surface state showing superconductivity. Now, as I mentioned before, this superconducting surface state comes from the indirect scattering process between the bands. Went over before, both elastic and inelastic scattering. So we could see that the surface state is superconducting. The nice thing about this is that this surface state is sort of isolated from the bulk in some sense. So you can call it a sort of floating 2D layer system, electron gas system, because this is not completely coupled with a bulk system. At the same time, you can still couple enough so that you can have superconductivity induced in the system. This helps actually in retaining the Majorana without being leaked away into the bulk of the system. That actually helps also in the system. So we have a nice, slightly isolated from the bulk 2D layer system, which is superconducting. Now the question is, of course, we need to tune the Fermi level in the system. That, of course, leads us to looking for the Majorana pair using STM. So then we, of course, we switch to completely STM studies. And what we have is a layer stack, as you can see here, the vanadium and the gold. And you take some region of the vanadium, and then you can see the atomic structure of the vanadium on one wall, as I mentioned before. Similarly, you can see that of the gold on top of the vanadium. You can see the atomic structure of the gold. Now, at the same time, you can also see the surface state of the gold surface, as you see from the STM studies and the conductance measurement. Now, you can see that the vanadium has a very nice energy gap, as you can see there by the STM. So these measurements are done around 360 millikelvin, and gap is about 0.83 MeV. That means by the STM study, as we saw in the case of planar junction, we have a superconducting vanadium observed on the surface. Now, we want to see the gold surface now with STM. So in order to do that, we actually pattern the gold into strips on the order of 100 nanometers or less. So those are the strips of gold. And then if you zoom into one of the edges here of the gold, then you see edge is very well defined, very sharp edge. Besides, it's a very nice atomic, it's a crystalline gold on the vanadium. So then you can again see all this atomic structure, everything intact. What is also important is after patterning all those things, the surface state still maintained, as you can see. It's on the order of 0.45, 0.5 electron volt. Now, at the same time, when it's cooled down, as you can see here on the right side, it actually shows also superconductivity. That means the gold surface is also showing superconducting behavior. So this is by the STM. So you have maintained, or we have indeed kept the surface clean enough to have both the surface state and superconductivity still present in the system. Now, the next thing is, of course, how to move the Fermi energy. Fermi energy is moved by adding European sulfide, as you see here. We have a very thin layer of European sulfide on the order of actually 1 to 2 monolayers. When you do that, we form islands of the European sulfide on the gold. You have the islands, then you can actually do the spectroscopy on the island and away from the island directly on the gold. You can clearly see when you do it on the gold, just bare gold here, you can see the typical 0.5 EV or something. as a surface state onset, whereas when you do the spectroscopy on the European Sulfide Island, you see this surface state has moved all the way down. I mean, rather, Fermi energy has moved all the way down. So you're only about 200 milli-electron volt away. This is only with 0.9 monolayer actually of European sulfide. So you're already able to move the chemical potential way down. Now, this actually nicely agrees with that what we see in the planar junction as well. There also you can see the surface state of the gold actually moved way down compared to the Fermi energy. I mean, yes, Fermi energy moved down way down closer to the band edge, the surface band edge. So we are able to move the chemical potential all the way down towards the edge of the band by having a thin layer of European sulfide. Now, this is very easy to understand because when you actually change the dielectric constant on the surface of the gold, you're actually changing the potential here, surface potential. That creates this big drop in the Fermi energy all the way down to the surface and all down to the edge of the band. That's because the European sulfide has a large dielectric constant, as you can see, around 24 compared to the vacuum or aluminum oxide. So we do have a way to actually tune the Fermi energy now. And the next question is about the interfacial exchange field or exchange coupling. European sulfide is one of those very nice compounds, magnetic compounds, wherein the europium ions have a moment of around 7 Bohr magnetons. When it's coupled with this gold, then you can have this all the charge carriers in the gold coupled to this magnetic moment, and then you can have a huge exchange field at the interface. This exchange field, in some cases, depending on what the material used and how well it's coupled, can be as much as hundreds of Tesla. In this case, we think it's at least many Tesla exchange field is involved in this at the interface of the gold. So thereby, we see now European sulfide actually creating not only this huge drop in the chemical potential, it also creates this huge exchange field at the interface. So this is some of the things we have done in the past, quite a long time ago. We have history of that. So you can see these publications in various articles. Now we have this nanowire of the gold, and then you have European sulfide on that, as you can see these islands. So now you start to looking into the behavior of what happens around the island. Once again, you can see that with 2 monolayers of European sulfide, you're able to move the chemical potential at the Fermi level very close to the bottom of the band, which is only about 30 milli-electron volt away. That's exactly what we wanted in the first place, to have very few modes available for the observation of the Majorana. So when you scan all around the island, what we find is you can see nice hard gap formation, as you can see here, all the way from 1 to 8, any position if you look in. This in zero magnetic field. Now apply a magnetic field along this direction, what we call as a north-south direction. Apply magnetic field, what we find is the gap is still maintained around, say, 7, 8, and 4 and 5, as you can see on the right side. So you have still the nice hard gap. Whereas when you go in this region and also in this region, we find that this a zero bias peak appears. What is important is we could not do the tunneling on top of this island, where we expect the Majorana to form at the edge here somewhere. Then we had to go away. This is part of the reason is this is a resolution becomes pretty bad, and then you cannot get good enough signal. So what we do is we go close to the edge, within about 1 to 2 nanometers away from the edge. So we are actually looking at the tail of the Majorana. So based on that, when we see this zero bias peak appearing at around, it starts appearing by about 3.5 Tesla, and it can, maximum field you can apply is about 4.8 Tesla. You can see this just in this region, and in that region you can see this peak appearing. Anywhere else, you still maintain this hard gap, so it hasn't changed. So this we attribute to the possibility of Majorana pair. This is better confirmed also in the next one, wherein we have an island formed at the edge of the wire. This is the gold edge, and then you have European sulfide forming. So this is this corner I'm talking about. Initially, again, all the way around 1 through 8, you can apply magnetic field. You find nice hard gap in all cases, as you can see here. Now apply magnetic field along this direction, again 4.8 Tesla. What we find is we still maintain a hard gap between 2 to 7, as you see here. All of the places you have this. Whereas in this corner, 1 and 8, you find that a nice sharp feature appears in the bias. That is, so this zero bias peak again is exactly opposite each other along the field direction. Once again, we say it's a Majorana pair formation in the system. So you can clearly see these Majoranas appear on the opposite sides of the island, whereas the rest of the region, nothing happens. So there's of course some filling of the conductance, because applied magnetic field also creates some extended states in the superconducting gap region. Now we can also see as a function of field, as applied field, both in position 1 and position 8, you can see as you increase the field, you go from hard gap, completely hard gap, towards sort of V-shaped curve, and then you start developing this peak, zero bias peak. As you increase the field, you can reach this nice peak. Whereas we could not go any further than that, because that's the maximum field available for us. So that same thing happens both for 1 and 8. The slight variation when the peak appears, in this case around, you can already see the peak here, where this one is takes a little bit of extra field to reach the peak region in the two locations. This particular island is about 60 nanometers this way and about 30 nanometers this way in this direction. Now, in order to see the transition from the actually hard gap state into the topological gap state, we can actually do a very fine scan of the magnetic field. Is a 2D plot, as you can see here from the hard gap, as applied magnetic field, you can see the gap closing and then gap reopening. Unfortunately, our field is just about enough what we have there. It cannot go any further than that. So you barely have opened the topological gap. In the middle, you can see this Majorana zero bias peak. So why we see this slight variation in the position 1 and 8, one can easily understand, because the weightage of this one is dependent on the factor what's called the gamma by gamma plus gamma p, where gamma is the typical tunneling rate, which is used STM, which is again very small for the STM. Gamma p is a quasi-particle poisoning state. So this is quite expected, especially very close to this region when the gap closes. That's when you have lots of these extended states, and also excitation across the gap for the quasi-particle is very large, and so your gamma p value is very high. So as a result of that, the weightage is actually very less now, and your peak is not very well defined. But if you go away from here, even further in the field, one should be able to see even better defined peak. So as you can clearly see how these things influence gamma, gamma p and extended, it depends on the location. So we cannot exactly have the same thing on both points. So this can explain why we are able to have a slight variation. Here also you can see the width is about half a Tesla, this width of this transition from gap state into the topological gap state. So now in order to see how far this Majorana peak actually extends, we can actually go away from this edge of the island. So that's where you see the Majorana peak, and then you go more away. That's what is plotted here. You're about 1 nanometer away from the edge, then you can see this nicely defined peak, and then as you go away by about 8 to 10 nanometers, you already hardly see this peak anymore. You see nice hard gap opening up once again. So this is away from here. Whereas on the side, if you move this direction, I already showed you, the gap open, nicely hard gap is maintained in all these regions. So in that sense, we can say that the localization is on the order of 8 to 10 nanometers for these things. Once again, I should point out that the actual Majorana peak would be somewhere here, main region, whereas we are not able to tunnel into that. So what we see is the tail of the Majorana. So if you go a little bit closer, or rather, if you're able to do on top of this, your peak will be much better defined. We are already away by about probably 2 or 3 nanometers. So now the modeling was done by, again, the group, as I mentioned before. For example, we have 2 cases here. One is on island in the middle of the gold wire, and the model calculation shows that the Majorana is nicely defined and along the edges, along the field direction. Whereas what you find, it is distributed, the Majorana wave function is distributed along the edge. So it means it's not concentrated at a single point as such. So that's what we see in our measurement. I'll show you in a second. Whereas if you put the island, indeed exactly what as we saw in the experiment, this Majorana wave function is really focused or concentrated at this corner where the European sulfide island intersects the gold. So this nicely localized, and whereas it go away from that, it actually weakens down tremendously. So in the case of island in the middle, you see a weaker Majorana this wave function distribution, whereas in the case of this edge happens to have an edge here, then you can have a stronger concentration. Now, if you look at the plot of the experimental result and compare with the theory, it's exactly what you see. You have an island which is riding the edge of the gold wire, then you see very strong peak developing. Whereas if you have an island in the middle of the wire, then you see the strength is weakened, as you can see here. So the second thing, of course, theory at t equal to 0, you see this Majorana peaks develop in the middle, whereas all these extended states or quasi-particle excitation can also give rise to all these extra peaks here. So if you're close to the topological gap, then this gap between the Majorana peak and the extended state is very narrow. So then there's a lot of influence from these states into the Majorana. So as a result of that, you won't see a well-defined peak. Whereas if you go to very low temperature and also in a superconductor which has a large gap, then you can have this extended state move far away from this. So you're able to see much better peak. And in the case of actually simulation, they find that although our measurements are around 360 measured temperature, then the peak is well defined. Whereas what we see is something closer to this. In other words, we have thermal broadening or even instrumental broadening. Our resolution is not so very good. So measurement, the filtering system and all that, we have to improve electronic noise in the system. It appears that although our temperature, base temperature 360, what actually probably system is seeing is around 700 millikelvin. That can also explain the breadth of the peak. So what is important is in order to get this kind of result in calculation, they have to assume an exchange field underneath the European sulfide on the order of 2 millielectron volt. Now we do have some open questions because this is one of the themes of this particular workshop. So these measurements, as I mentioned, it's done 2 years ago, and we still have to improve on this, and also at the same time, we to reproduce this one in other systems, for example, with other stronger superconductor, creating a bigger gap. And we need to have also better defined signal and also the robust signal in the system. Thirdly, of course, we need to go to higher magnetic field, and we have to do some angular dependence, and of course, at a lower temperature possible. Then these are all with the STM, for example, or STM spectroscopy, scanning tunnel spectroscopy. Whereas if you want to actually take it to the next level, talking about the qubit formation, then you have to create nano junctions for these things with a top superconducting electrode. And of course, this can lead to parity measurement in the system, and then of course, topological qubit in the system. So to summarize this one, what we have seen in the case of gold surface state, when you drive into the superconducting state, you can actually see signatures of Majorana pair formation in the magnetic field. And the good thing about the gold system is that it has a very large Rashba split, spin-orbit splitting, and which is 1,000 times bigger than what is out there in any of the semiconductor system deal with. And nice thing also, this is you can grow this gold epitaxy very easily on many of the metals. So that gives us lots of freedom to choose the layering what we want. And then of course, nanofabrication is also easy, because we already shown that we can create small structures and we can have any kind of architecture in the system, complex network. So it all boils down to the fact that in this metallic system, there may be a good possibility of actually creating qubit architecture. So here is some possible nanostructures we can make the gold. As you can see, it can go down all the way to even 60 nanometers gold with a simple SEM-based lithography. That's our system. Part of the reason we are not having the fantastic stability and all that, because this is sitting on the second floor, this kind of sort of very simplistic way of isolating, vibration isolation, the layers of sand and all those stuff. And another thing is, of course, we have not optimized the filtering system, electronic filtering. That's what we are working on right now. And we do have a fantastic capability of creating any kind of layer system here. We have already been able to do this in some of the superconductor as well. With the bigger gap, we can actually see surface state superconducting. So that is ongoing work right now. And of course, the next thing is, of course, where we take this from, right? So we can talk into topological qubit. Majorana, if happens to lead to the qubit, then it could be a good solution for a decoherence problem in the superconducting qubit. So we are planning to follow the architecture or the model by Liang Fu in group. And our goal is to actually say, suppose it's a high risk problem. And our goal is to actually create various circuits, as you can see here. So we want to measure the parity by measuring the current through the loop. And we can do by both by flux or also by conductance measurement. These things. This is this plan we have. So with this one, I want to thank you very much for your attention.
Thank you for the wonderful talk. Are there any questions from the audience? Please write your name in the chat so I can give you the permission to talk.
I have a question.
Yeah, so sorry.
Yeah. Okay. Yeah. The question is how important do you think is the one-on-one direction? Why one-on-one? How about some other orientation? What is the role of this particular orientation for this scheme?
Okay.
Do you think this is relevant, or it just happens to occur?
No, it's important because this is the direction in which the Rashba splitting is largest. There are other systems too, which have a surface state, which have a large Rashba splitting. But again, the good thing about the gold is it really can grow on many things, number one. Number two, it's inert surface. For example, you talk about bismuth, or we can talk about lead, or any other system, or silver. These are all have surface problem. So dealing with that is going to be a little bit of difficult situation.
Yeah, actually, my question is, do you think the one-on-one, why one-on-one is critical? If it's, let's say, 1-on-0 or some other orientation, do you think the effect will be much smaller, or what do you think?
That's very interesting question, because it's true that you can have any orientation you want as long as you have a large spin orbit. Second thing is gold forms very readily 1-1-1. So why you want to go for a difficult thing when you already have a system which has the best properties?
Okay.
Okay. Hazra, you wrote a question. Do you want to ask it?
Sure. I was just wondering, in the island that which had the island on the border. So you showed that at 3.5 Tesla there was some difference. You don't see the zero mode at one edge. Do you see it at somewhere else, or is it just missing at that magnetic field?
No. As you saw before, see for example. See for example, take this for instance. The transition is about half a Tesla. We're going into the topological state. That means it's not really like one number. Okay, the field that is a critical field beyond which it becomes topological. Secondly, as I also see on the left side here, there are a lot of other factors involved in the observation of the peak or not. What other factors are involved in that corner? So having this small distribution in the field, I don't think it's a major thing. It's a typical materials, right? You had to process these things. So they're all
right, but in a given sample, shouldn't you be seeing them appear and disappear together, even if they vary, if the critical field varies from sample to sample?
Yeah, they do appear together at the same time. As you can see, the scans are done in
Okay. Please mute yourself if you are not speaking.
Okay, so you do.
There was another question from Seongshik. Oh, you want to answer? Sorry.
No, I was saying, you could see them appearing at the essentially same time, although not simultaneously. You cannot measure with an STM tip, so you can only scan one after the other. At each field, you can actually scan two sides.
Okay. Seungshi,
Yeah, I already asked question actually earlier. Yeah, that was me. Yeah, earlier.
So it was asked. You don't. Yeah, I have one question then. So how many transversal modes you have in this below the europium sulfide?
Yeah, so for example, it depends on where the how far the Fermi energy from the bottom of the band, right? In this case, it's estimated to be around 5. Whereas if you have
5,
right, if you have regular 0.5 eV away, then it's hundreds of modes.
Okay, so you say 5, yeah. That's
yeah.
Yes, sorry, you already asked, right? You have additional question?
No, I didn't ask. Hi, everyone.
No, okay.
Thanks for the nice talk.
Thank you.
I had a question on your slide 16 where you showed tunneling spectroscopy from the planar junctions and your model where you assumed that the aluminum density of states is not spin split. And I was wondering, what is this assumption based on? Actually, I would guess that the aluminum density of states is spin split, and then you actually have 8 coherence peaks participating in the spectroscopy.
Right. Yeah. So I think you're talking about this one, right? Now,
yeah.
Aluminum is very thick. When you have a very thick aluminum, in this case, the aluminum is about I don't know, 20 nanometers, something like that.
It says 10 here in the corner.
Huh?
In the corner, it says 10. Or
oh, sorry, 10. So, and you do that, what happens is the splitting becomes a little bit not easy to see. You can see the splitting very much nicer when you have a very thin layer. So if you go to very low temperature, you can see it. But in this case, the temperature is too high for observing this splitting. The resolution is not enough here.
What was the temperature that you measured at?
This one measured 1 Kelvin, as you see.
Ah, okay. So, okay, good. So that might explain it.
Right. So the TC is about 1.7.
Got it. All right. Thanks.
Yeah.
Thank you, sorry, for the questions. More questions from the audience? If not, let's thank the speaker again, and we move on. Thank you. Thank you for your talk.